In the vast expanse of our universe, astronomers have made a discovery that challenges everything we thought we knew about cosmic evolution. Using the revolutionary James Webb Space Telescope, scientists have identified a supermassive black hole that existed just 400 million years after the Big Bang, far earlier than our current models can explain. Join us as we explore this cosmic mystery, understand why it's forcing scientists to rewrite the rulebook of astrophysics, and discover how this ancient giant might transform our understanding of the universe's origins. The James Webb Space Telescope has once again proven its worth as humanity's premier cosmic observatory. In a groundbreaking discovery published in Nature Astronomy, astronomers have identified a supermassive black hole with a mass equivalent to several million suns and a galaxy designated UHZ1. What makes this finding so extraordinary is not just the black hole's enormous size, but when it existed, merely 400 million years after the Big Bang, when the universe was in its infancy. This timeline defies our current understanding of how black holes form and grow. According to conventional theories, black holes should start small and gradually accumulate mass over billions of years, not reach such enormous proportions so early in cosmic history. This discovery has sent shockwaves through the scientific community, forcing astrophysicists to question fundamental assumptions about the early universe. This discovery directly challenges three major theories of early black hole formation. The first theory proposes that black holes form from the collapse of early massive stars. When these giants exhaust their nuclear fuel, they collapse under their own gravity, potentially forming black holes with masses up to 100 times that of our Sun. However, the newly discovered black hole in UHZ1 is millions of times more massive than our Sun. The math simply doesn't add up. There hasn't been enough time in the universe's history for a stellar mass black hole to grow to such enormous proportions through conventional accretion processes. It's like finding a 100-year-old redwood tree when the forest is only 10 years old. The timeline makes it seemingly impossible. The second theory involves the direct collapse of massive gas clouds into black holes, bypassing the star formation stage entirely. This model suggests that instead of forming stars, some primordial gas clouds collapse directly into black holes with initial masses of 10,000 to 100,000 solar masses. This would provide a significant head start toward reaching supermassive status. The challenge is that this process requires very specific conditions that scientists previously believed would be exceptionally rare in the early universe. These conditions include the absence of elements heavier than hydrogen and helium, along with specific radiation environments that would prevent fragmentation of the gas cloud. Finding evidence that such conditions might have been more common than thought could revolutionize our understanding of the early cosmos. The third theory suggests that dense star clusters could merge to form a massive black hole. In this scenario, the crowded centers of early star clusters would see stars collide and merge repeatedly, eventually forming a massive object that collapses into a black hole. However, like the other theories, this process was thought to require more time than the universe had aged when the UHZ1 black hole formed. Just 400 million years after the Big Bang, there simply shouldn't have been enough time for sufficient stellar evolution, multiple mergers, and subsequent growth to create a black hole of millions of solar masses. As Dr. Akos Bogdan of the Harvard and Smithsonian Center for Astrophysics, who led the research team, noted, this observation forces us to consider that either black holes can grow much faster than we thought, or they can start from seeds that are much more massive than the remnants of individual stars. The detection itself represents a remarkable technical achievement for the James Webb Space Telescope. The black hole wasn't observed directly, an impossible feat at such distances. Instead, astronomers detected X-rays produced by superheated gas falling into the black hole. What makes this detection even more impressive is that these signals were amplified through gravitational lensing, a phenomenon where the gravity of a foreground galaxy cluster bends and magnifies light from distant objects. This natural cosmic magnifying glass enhanced the signal from the distant galaxy, making the detection possible despite the immense distances involved. The research team employed a multi-wavelength approach, combining JWST's NIRCam instrument with supplementary data from the Chandra X-ray Observatory. This combination provided crucial evidence that the X-ray emissions came from an actively feeding supermassive black hole rather than other cosmic phenomena. JWST's infrared capabilities allowed researchers to observe the host galaxy's properties, while Chandra's X-ray vision confirmed the energetic processes associated with material falling into a black hole. This discovery highlights the unprecedented capabilities of the James Webb Space Telescope, which was specifically designed to observe the earliest galaxies in the universe. Its advanced instruments can detect light that has been traveling for over 13 billion years, providing glimpses of cosmic history that were previously inaccessible. The telescope's sensitivity and resolution have already surpassed expectations, with this black hole discovery being just one of many groundbreaking observations in its early operational period. JWST's ability to observe in infrared wavelengths is crucial for studying the early universe, as the expansion of space stretches ancient light into these longer wavelengths. This technological marvel is allowing us to push back the cosmic frontier, observing objects from when the universe was just 3% of its current age. The telescope represents humanity's most powerful time machine, allowing us to witness the conditions of the universe when it was in its infancy. This discovery has profound implications for understanding how galaxies and their central black holes co-evolved in the early universe. Current models suggest that galaxies and their black holes grow in tandem, with each influencing the other's development. The mass of a galaxy's central black hole typically correlates with the mass of the galaxy's central bulge, a relationship observed consistently in the nearby universe. However, the black hole in UHZ-1 appears disproportionately large compared to its host galaxy, challenging this established correlation. This suggests that the relationship between galaxies and their central black holes may have been fundamentally different in the cosmic dawn era. Perhaps black holes formed first and helped shape the galaxies around them, rather than growing together simultaneously as previously thought. This finding could completely reverse our understanding of the relationship between these cosmic structures. The observation also provides a new data point for understanding how the universe became reionized, a critical process where neutral hydrogen was transformed into an ionized state during the first billion years after the Big Bang. Radiation from active black holes, like the one in UHZ-1, may have contributed significantly to this process, helping to shape the universe as we know it today. The intense energy output from these early supermassive black holes could have been crucial in heating and ionizing the intergalactic medium, affecting subsequent galaxy formation throughout the cosmos. As these black holes devoured surrounding matter, they would have released tremendous amounts of high-energy radiation capable of stripping electrons from hydrogen atoms across vast regions of space. If supermassive black holes were common in the early universe, they may have been primary drivers of this fundamental transition in cosmic history, rather than just passive participants as previously assumed. Furthermore, this discovery may help explain the existence of extremely massive black holes observed in quasars from when the universe was just 700 to 800 million years old. These objects, with masses billions of times that of our Sun, have always been difficult to explain within standard formation timelines. If black holes like the one in UHZ-1 were common in the early universe, they could have been the foundations for these later ultramassive objects. They would provide the seeds that could grow into the billion solar mass giants we observe powering distant quasars. This connection between early supermassive black holes and later ultramassive ones could solve one of the most persistent puzzles in cosmology: how quasars managed to achieve such enormous power so early in cosmic history. The UHZ-1 black hole might represent not an anomaly but the missing link in our understanding of black hole evolution throughout cosmic time. Researchers are planning follow-up observations of UHZ-1 and searching for similar objects to determine whether this black hole is an anomaly or representative of a previously unknown population of massive early black holes. The JWST's ongoing survey programs will likely uncover more such objects, potentially establishing a new understanding of black hole formation and growth. Each new discovery will add another piece to this cosmic puzzle, either confirming that UHZ-1 represents a rare exception to the rules of cosmic evolution, or indicating that our fundamental theories need complete revision. Scientists are already designing new observational strategies to specifically look for these early giants, using combinations of infrared, X-ray, and radio astronomy to identify their unique signatures. The race is on to find more of these cosmic anomalies, with research teams around the world analyzing JWST data for similar objects that might be hiding in the early universe. This discovery exemplifies how advancing technology continues to challenge and refine our understanding of the universe. Just as Edwin Hubble's observations a century ago revealed that our galaxy was just one among many in an expanding universe, the James Webb Space Telescope is showing us that the early cosmos was far more complex and dynamic than previously imagined. The massive black hole in UHZ-1 stands as a cosmic enigma, inviting scientists to develop new theories and models that account for its precocious growth in the universe's infancy. As we peer further back in time with increasingly powerful instruments, we may need to fundamentally revise our understanding of how the first cosmic structures formed and evolved into the universe we observe today. This single discovery has the potential to transform astrophysics in the same way that exoplanet discoveries revolutionized our understanding of planetary systems. What was once thought impossible or exceptional may turn out to be common in the early universe, forcing us to reconsider the fundamental processes that shape cosmic history. The discovery of the supermassive black hole in galaxy UHZ-1 represents one of the most significant challenges to our understanding of cosmic evolution in decades. Existing just 400 million years after the Big Bang, this ancient giant forces us to reconsider the timeline of black hole formation and growth, the relationship between black holes and their host galaxies, and potentially the very conditions of the early universe itself. Whether black holes can grow much faster than we thought possible, form from direct collapse of massive gas clouds, or originate from different processes altogether, this discovery opens new avenues of theoretical and observational research. As the James Webb Space Telescope continues its mission, we may find that UHZ-1 is just the first of many cosmic anomalies that will ultimately lead to a profound revision of our cosmic origin story. In science, the most important discoveries are often those that don't fit our existing models, and this ancient black hole may prove to be exactly the kind of beautiful anomaly that drives scientific revolution. By pushing the boundaries of what we thought possible in the early universe, it reminds us that the cosmos remains full of mysteries waiting to be unraveled. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.